I'm gonna close my eyes and count to 10.
Discussing stability.
I'm gonna close my eyes, and when I open them again, everything will make sense to me then.
So the pleasant surprise of dynamical system theories that not only topology is invariant, meaning if you have solutions in state space that, for example, periodic solutions could be intertwined, they could form braids, etc. And that has to be invariant under any change of coordinates. But not only that, there is even metric invariance. Distances in some sense are invariant, but it's very important they're actually not distances, but the ratio of distances. For equilibrium, if we could describe the behavior of a neighborhood by a very simple formula for the Jacobian in a neighborhood. So if you start at equilibrium point xq, the distortion of the neighborhood is described by stability matrix or matrix of velocity gradients. And this was computed at the point q, so that doesn't change in time. It's a simple definition of Jacobian as exponential of stability matrix integrated in time, works without any fancy time ordering or anything. And that means that if you understand the spectrum of eigenvalues and corresponding eigenvectors, of the stability matrix, we also know the spectrum of multipliers. Which are the eigenvalues of Jacobian, and that's simply the ith one is simply e to the t, the eigenvalue, ith eigenvalue of the stability matrix, and the multipliers have the same eigenvectors. So once we have solved this problem, we have also solved the problem Jacobian. For periodic orbits, thanks. The computation of Jacobian is a little bit more involved, but once we have a Jacobian evaluated on the periodic orbit, it's a matrix, d by t matrix, that cares where we start on the periodic orbit. And then it runs for one period, so we just label it by the label for prime periodic orbit. That has multipliers, like every other Jacobian matrix, d of them, real or complex pairs, and eigenvectors, but now these eigenvectors depend on the point at which we compute the Jacobian. So x is in the orbit, so set of points that belong to periodic orbits. So it's a one-dimensional curve that m means some set and p means it's labeled the word will mean prime, as you'll see in a second. And one obvious thing, now, to me, totally amazing thing is that this does not depend on the matrix. It only depends on the orbit itself, on the geometrical object. So these numbers are characterizations of orbit, and that'll be the main thing I want to prove today. And the eigenvector and matrix itself, they depend on where you're on the orbit. They will change as you move along the orbit. You know already one of them. So for example, one of the eigenvectors is always the velocity. I showed it before, point x. And this obviously depends on what point we are on the orbit. Now the general thing you can say about the multipliers and the exponents is that you can classify them, and it's useful classifications. So types of stability. You can always sort the set of multipliers of these numbers, real or complex, into three sets. Expanding, marginal, contracting, and contracting. Lambda expanding, these are all multiplier let me say that E is also the number of expanding, such that the magnitude of the multiplier oh God. I'm trying out new notation. These things are defined as macros in a book. If you hate them, I can redefine the whole book at one go. But the ith exponent in this set is strictly smaller than 1, cannot be 1. The marginal guys, of which we know we have 1 always, and I'll use notation parallel. What is it?
Expanding value size
should be larger than 1. Thank you, Burak. Not thanks the rest of the class. I mean, this was totally criminal. Remember what that English teacher discovered. And there might be more of them, but there is definitely always 1. You know, meaning, I'll call it longitudinal. It's a bad word I learned in quantum field theory, but you know, it means it's parallel to the flow, such that anybody in this set has magnitude strictly 1, and it can be complex. So it could have a form Li is e to the I omega that I didn't write here. In general, we can associate with each one of these things a sign. And then compute the rate per unit time in the cycle, the real part plus minus the imaginary part if it's a complex thing. So it can be complex, in which case you say you have an elliptic stability. If you perturb something, it just runs on a circle or an ellipse around your periodic point. And finally, there could be contracting. So there's a set of these. Now the marginal ones, if you just take any matrix, there's a probability 0 it'll have eigenvalue 1. Yeah. That just won't happen. There's got to be a good reason to have eigenvalue of a certain type. And there are two reasons. One is symmetry. So when you have continuous symmetries, and the one that we already discussed once has to do with that the orbit is not changed by moving points on it forward in time. But there could be, rotational symmetries, spherical symmetries, SU3 symmetries, E8, all kinds of weird symmetries could exist. Each one would have a marginal eigenvalue associated with it. And finally, the contracting ones, I don't know what to label them as, some label. The final one is the set of the set. No. It's a d-dimensional system. The contracting ones, sweetly enough, we don't actually mind if there are even infinitely many contracting ones. So the theory that I'll develop for you works as long as there's a finite number of expanding ones and a finite number of marginal ones and any number of contracting dimensions. And for that reason, even though I'll teach you, ridiculously silly things, I'll show you a parabola, a billiard in a plane, and Rosslare attractor in 3 dimensions, the thing that you're computing. We actually use this theory in infinitely many dimensions for dissipative partial differential equations like Navier-Stokes. And if you don't like, some people don't like these multipliers. The problem with multipliers is that when the period gets large, the multipliers can be very big. And it's hard to write them on a piece of paper. While these things are rates per unit time, and typically in healthy systems, these rates are finite numbers and nothing too big or too small. So often it's convenient to use exponents rather than multipliers to specify stability of dynamical systems. And then there is a weird thing that it turns out that sometimes these multipliers also have minus signs, which I don't know how to write in this particular way. Yeah. So you write them out here. Now if you like the exponents, then this classification is that the expanding ones have mu I positive. Contracting ones have mu I exactly 0. So this part is set equal to 0, though you might be running around. And marginal ones. And the contracting ones are strictly contracting, or their real parts of their exponents, Floquet exponents, are negative. So all I ask for you in this course is that you don't mix up big lambda and the exponent. You know, a number and its logarithm are very different things. But literature is confusing if you look at other literature that people who haven't yet started following ChaosBook, that might use random letters for everything. So you'll just have to sort it out for yourself. Because everybody uses dynamics, and engineers like other letters, then control engineers do something and pure mathematicians do something else. But this is the basic classification. So now, when you have this classification, you would say, well, is this invariant classification? So when you tell me that this orbit looks unstable in laboratory frame, if I go to some other frame, is it still going to be unstable? Can I stabilize it just by changing coordinates? It's not obvious a priori. And now the beautiful, amazing thing that I want to spend some time on right now is that not only is this sign preserved by any choice of coordinates, but even the magnitude of these factors, exact values of this factor, have invariant meaning. And this is very important for us, because when we do research, we have to agree with our colleagues whether we are looking at the same orbit. And one signature whether we have found same solution is to look at its period. But the period actually depends on your clock. And it's quite legal to even redefine time in all kinds of weird ways. Only thing that time does is it's giving you ticks along this orbit. And for example, when you're solving problems in celestial mechanics, like a comet going into the sun and coming out of the sun, so an ellipse which has infinitesimal width is long. This actually is solution of Kepler or Newton equations of motion. It's Keplerian ellipse. And in those cases, it will be very hard to do it numerically, but you can redefine the time in such a way that you use different clock rate depending on how far you're from the center of your, center of mass of your system. And it works. It's perfectly fine. So time is not sacred. And we are totally used to the idea that X, Y, and Z are not sacred, because depending on the symmetry problem, you might prefer to do it in R, theta, phi, or it's totally arbitrary. These numbers are invariant. Now the reason why they're invariant, I'll first draw a little picture and then do some algebra. But the picture is one that you're very obvious, very used to. So if I have my state space M, and you have your state space, and I have my coordinates and you have your coordinates. Then if these are the same dynamical space, then if point here is in M and your point is in the redefined system, then there is a mapping that tells me how I change these coordinates. Tells me that y is, now this is a vector, this is a set of functions, h of x. And this mapping, at least locally in some patch where I'm working, should be one-to-one diffeomorphism, so I should be able to go back and forth as I wish. I should also be able to go back to x, saying this is h minus 1y. And now what happens is when I go back, your coordinates look a little bit weird. So I can think of this that transformation from one set of coordinates to the other one is like taking a piece of rubber and stretching it. So, the things line up. And the stretching and deformation is described by this h, and of course this happens in d dimensions, so this is a big deal. And this is called a smooth conjugacy. Conjugacy is any relation where I can go back and forth. So if I have set of points here, I can uniquely assign the set of point to them back and forth. But it can be something that's called topological conjugacy, in which case, people in a different department here love this stuff. So they're usually no-place differentiable functions that tell you how you go from here to there. So they can be totally horrible. But for us, we will insist that conjugacy is smooth, so we can take derivatives of this map, at least one and hopefully all, but definitely at least one. So then, when we are computing a Jacobian matrix, what we are doing is we are looking at an interval, in this coordinates, dx I going in one way at 0. And then what dynamics does to that interval, it goes around, and if this interval is attached to a periodic point, then it'll come back to us including the periodic point. So here is a periodic point x that has a property in our dynamics. You come back after a period if it's on a cycle. So what this matrix is doing, it's computing all the ratios between dx, this is delta x when it comes back, and now if you keep the point fixed and we stretch its neighborhood so it agrees with the neighborhood in the new coordinate system. So this is yp, where this particular point y, well, it's given by this relationship. What we are doing is we are stretching the neighborhood, and we do this only once. We don't time t later stretch it differently. So the stretching of the two neighborhoods is the same, and in infinitesimal neighborhood periodic point, the stretching factors cancels. So that's the moral reason why this matrix will produce invariant quantities, but in detail it doesn't really look like that because it turns out it's a similarity transformation. So the eigenvalues are the same, but not. So that's the main idea. Now I'll work out the algebra for it. I'll do it in 2 steps. And the first step is really the subset of the second one, but it looks a little bit different. So the first thing that's comforting about periodic orbits is that Floquet exponents, not exponent, multipliers or exponents. The multiplier is the natural object for dynamics. Floquet multipliers, same everywhere. Along the periodic orbit. So what's a Floquet multiplier on a periodic orbit? I take the matrix, I value it at point x, Jacobian matrix. I go around the full period, and I denote this by putting a subscript p. And the multipliers and corresponding eigenvectors satisfy that eigenvector at point x, so d-dimensional vector, just returns a number so it's a property of prime orbit, but in this argument I'll omit the subscript and just say the ith multiplier. So that's a Floquet multiplier. Next, time. Evolution in time is an abelian group. What does that mean? I showed you last time that, or a few lectures ago, that Jacobians have a group property that if you go for time t and then time t prime, having started at some point, that's the same as a product, so that's just a group product. I go first time t prime, starting at my initial point, and then I go to the image on the trajectory. So this is x at time t, and this is x at time, well, that's just x element of the periodic orbit. This is where I'm time t later. And the way we have done this is that so that's a group property. Jacobians multiply along the floor. But this is just a real number, so I can split it. I can write it as t prime plus t. So that's the same as going time t, arriving at f t of x and going T prime. So that's a group, and this is a abelian group.
Okay.
Yeah.
The JP of that's in the first line, the Floquet multiplier, that should have the superscript for the period, yes.
Yeah, I'm using a shorthand notation. I'm defining the particular Jacobian where I go the full period around for x for any point in the cycle. Instead of writing it upstairs, I just write it with a label there. Because it happens so often, it's convenient. It's a kind of central object of the theory.
Is the Floquet multiplier JP or lambda?
Floquet multiplier is lambda. Usually you would put a subscript p here denoting belonging to a particular orbit. And what was the question?
Oh, I mean, the question is the Floquet multiplier is...
This number.
Yeah.
And Floquet exponent I've erased, but it's logarithm divided by time. So now I can use this, and I can multiply both sides of this equation by JT So let me call this point x prime.
Sorry, can I have one question? So it's a question about notation. The EI is the vector that is tangent to the flow at the point x.
This one?
Yes.
Yeah, this is a matrix. We evaluated it at the point x on the periodic orbit. At that point, matrix is a bunch of values, d by d values. And it has an eigenvector which is computed at that point.
Right. Which should be the E should be the tangent vector to the flow.
No, that's there are d. This is d-dimensional matrix, so there is d different eigenvectors, and one of them happens to be tangent. The rest are not. Actually, it's very important that d minus one of them are either transverse or marginal. So this is a complete set of eigenvectors. If we go to some other point, matrix changes and the eigenvectors change. And what I'm doing now is I'm giving you the relationship. I'm saying that if I compute it at any point on the cycle, I know it every place. So what I do is I multiply both sides by jx prime. So this is, this point, t prime, t prime. And, write this equation again. So now put the period up there explicitly, as Chris wanted me to do. Starting at the initial point, x, multiplying EI x plus lambda I and this is, I will do this at home by hand because I'm making an error. Put a video from home, but anyway. JT So I've done nothing, I just multiply both of them.
Those multiply by t or t prime. In your picture, you
Yeah, okay. See, how did I do it? It's totally trivial. I want to use the period. I'll make one of these guys t. And I'll call this point x prime. So I want to use that this is go time t from x bn x prime, the period, and for brevity I'll, because we only have one prime cycle, I'll forget the subscript for a while. This is the same as jt, go a whole cycle around. Okay, so I'll let you digest this for a while. The point is, because the orbit is periodic, I end up at the initial point after period t, so here I advance from the initial point. But I can rewrite this as initial point going finite time and then the whole period at x prime. That's the whole trick. So I multiply these guys using this formula. Modernity. I know, modernity cannot be controlled. So, so now here I use my relation that this can be written as TP Jacobian at x, multiplying that I'll call I don't know, tilde I of x equals lambda I ei of x, but this tilde object is just the initial vector simply transported finite time t by the finite time Jacobian. So what do we find? That computed any place along the periodic orbit, we have the same equation with same multiplier. And that's not really obvious because, when you go around the periodic orbit, there could be lots of stretching here. It could be really wild around here. And maybe it could be very boring down here. As it often happens in time in human relationships and other things. So, a priori it's not obvious that computing deformation here and deformation in the quiescent period will give you the same ratio. So that's a very comforting, nice result. That if you solve your eigenvalue problem any place on the loop, the eigenvector, it's being moved or covariantly transported or whatever along the loop just by Jacobian itself, which you know how to compute. And the multiplier is an invariant property just of periodic orbit of the whole set, even though you compute it in particular coordinates. So that's the first nice result. The second nice result is implementation of what I'm just erasing right now. Not only is Floquet multiplier the same computed any place in my coordinates for my periodic orbit, but in Japan they'll get the same multipliers, even though they use, totally strange coordinate system where they've used Mayer G and hypergeometric transformations to go from my stupid coordinates to the very elegant coordinates. So, okay, multipliers invariant under huge group of transformation, which is, the general group of transformation general relativity, under all smooth conjugacies. Now this is much more ambitious than, you changing coordinates by rotating them by 45 degrees or going to polar coordinates. This is all possible. Transformations which are not mutilating the dynamics. They're smooth enough, the dynamics is the same in different coordinate system. So here we are, the stuff that I just erased. I have a function, I have a set and a mapping. So my dynamics is defined as state space and law of dynamics on it. But your dynamics is defined as m tilde g so you have a different state space and you have what looks like a different law of evolution written in your coordinates. And they are related by y is h of x. So, to be very lazy, suppose that our state space was one-dimensional and this dynamic was just mapped from a line onto itself. So for example, you take a point on a line, you square it and add 3. That's an example of using a nonlinear map on the interval. And this is parabola, so you can take square roots of it, so you can go back and forth and define mapping both ways. Simplest possible example. And now what you would like to know is if you have a fixed point in your original system. So if your original function was f, and this is where you are at time n, and this is where you are at time xn plus 1. So, so you have simple 1D dynamics. Xn plus 1 is just a function of xn. Then the fixed point, xq, will satisfy that you're there forever. So this is your fixed point xq in your original coordinate space. And we are studying Jacobians. Jacobian is the derivative of, where you are at later time to previous time, and that derivative is just the slope here. So Jacobian, it's 1-by-1 matrix. So you can just write as a multiplier. Evaluate it at the fixed point Q of your map. So now in Japan, they have a different function g, which is obtained by replacing my x by h of x. So to me, it's not obvious that they will find the same stability in Japan as I find here. Now, if I have this relation, then this map G, the map in Japan, can be written in the following way. I want this to be function in Y space because, all the points here are Y points, elements of tilde space. That means that I want to look at G of H minus 1, no, actually, H of X. And I'll just write the result. The result is that the map in this space is obtained by going from y coordinates to h coordinates, which is h minus 1. Using the result as the argument of the function in this space, and then going back from x coordinates to y coordinates. So can you live with this? So if it were just rotations, what we would do is we would first, rotate from x to back to y, so we have to go counter-rotate, then we would do whatever we do in our lab frame, then I'll rotate it back. But the relation is actually a functional relation. In that case, I would have product of 3 matrices or something. But in general, I go from y to my coordinates here. I apply my law, which is a mapping of x. So this means I'm looking at f of x.
So should first it should be the h?
This should be h. Thank you. Then I've gotten my result of my f operation in my coordinate x. So to come back to the y world, I have to change coordinates again, right? So this is h of f of, and x itself is h minus 1 of y. So are you happy now? But it's, more elegantly written as a functional composition. So now I'm still in one dimension, and my question is, in my new coordinates, in this world here, I would like to know what is the map looks like something else. It's single valued, sorry. So this is yn plus 1, yn. And this is the law of motion in the new coordinates, and the fixed point in the new coordinates should be someplace on the diagonal here. So this is YQ, which is the image of X in Japan. And I would like to know the slope. What is G prime evaluated at YQ? So now what I do is I take derivative with respect to y of both sides of the equation. So I'm interested in G prime, which is d dy of h of f of h minus 1 of y. And now I can use chain rule. This is a function of a function of a function, so it'll be product of 3 derivatives in a chain rule. So the first one is derivative of h with respect to h is this map here, so it has to be with respect to its argument, which is where I'm in this space. Evaluate it at f of x, but I'm at a fixed point, so this is evaluated x cubed. Then this has to be multiplied by chain rule by derivative of f with respect to its derivative. So this is f evaluated at x. This by definition is x, so that's good. X cubed. And I want to evaluate this as a new point. And then I have to take derivative of this guy. So I have to take derivative of d dy of h minus 1 and evaluate at yq. Are you okay? So now this object is 1 over h prime. And I'll let you, if you don't remember, I'll let you be an exercise. That has to be our x cubed. These two guys cancel, and we prove that the slope of the map GYQ equals the slope of the initial map computed at x cubed. In other words, multiplier of 1 by 1 matrix, Jacobian matrix J, is lambda and invariant. So, to me this would not be obvious because functions look totally different. A fixed point is a different place, etc. And the reason why it's true is this rubber sheet argument from before. When you're looking at the neighborhood, you're looking at any interval divided by, what is it, after one iteration, And if you stretch the neighborhood, you'll multiply both infinitesimal intervals by the same deformation number, and they'll cancel out. So this, relates to Kimberly's question. This invariance doesn't know about length. This is just intrinsic to dynamics. We have never defined notion of length and norm, etc. To you, it might seem trivial, but later on, what is norm is totally not obvious. So now I think the remainder I'll let you do as a problem set. So this is the spirit of the whole calculation. But in d dimensions you have to work a little bit more because this is a d-dimensional thing, this is d-dimensional thing, and every time you take derivative, you'll get d by d matrix. So I'll just tell you what it looks like in d dimensions. You'll get that Jacobian, d-dimensional version of the slope. So Jacobian in the Japanese world, for the computed at a fixed point x, y, q, so the fixed point someplace here, so you came back and this is a fixed point, is the Jacobian that you computed in your coordinates, xq, so not tilde here, just Jacobian. And then this guy here turns out to be a matrix of derivatives, so I'll give it some, I don't know why, but in book I call it gamma. This can be changed. And it's computed at f of x. So this is a matrix AJ, this is IL, this is L, M, and then there is inverse of this matrix GM at M, J, summed over L's and M's. So this is matrix multiplication. So general statement is like that. They're actually quite useful. And the book looks wrong. I think this should be Y. So this is how any finite time Jacobian transforms if you start at point x and you go some time t. Okay, I'll put t here. Or in the new coordinates, you start at the image of x and go time t. That finite time says that you have to compensate for the initial point here, and then you have to, you pick up a term of, this is from inverse mapping, and then you pick up the term of where the final point is along this trajectory. You have to go to y coordinates. But, so this is just a rule. You give me your flow, you give me your transformation h. I can compute this. I should have defined it. This matrix X K is the new coordinate, the old coordinate. Or if you wish, you can write it as h of x to make it more explicit, xk. And the other one, so, by the way, anybody, 20 people seem to have been on Piazza or something. If you hate that thing, we won't do it. But instead of sending me an email saying that, you know, I made an error in problem set, etc., if you put it first on Piazza, then your alert colleagues will set you straight or set me straight. But, you know, some people say it works, like Burak says it works. So you're all on Piazza and, you know, you use it. And here's an example. What you could say, I think the book is wrong, what it writes. This part is correct, but the inverse should be a function of y, I believe, just looking at this. And it should be, you know, the inverse transformation, dx dy, which is d of inverse operation I of y divided by dy. So you do curvilinear transformation, but locally you just keep the linear part of it. So you go from the coordinates in Japan to coordinates in Georgia. You compute the linear deformation of your neighborhood in Georgia. The result is a point along the trajectory time t later. You reconvert this using the derivatives to linear approximation derivatives, and you get Jacobian and new coordinates. Now, if f of t, let's call it this, f of t of x is x. So this is equilibrium of fixed point. Well, actually, in my notation, this is always called fixed point. Then this is being evaluated at the initial point because I came back. And in that case, I have that the G minus 1 is inverse of G because it's matrix evaluated at the same point. That means I have a similarity transformations. And you know that if two matrices, so one way to compute eigenvalues is to take your matrix and solve the eigenvalue problem. Okay, let's call it J to be very suggestive. But you know, I'm allowed to multiply this by 1, so I'm allowed to write this as determinant of d by d matrix times its inverse times J minus lambda I. That's just multiplying by 1. Then I'm allowed to use cyclic property of determinants and traces to write this as determinant of gamma J lambda minus. So on the similarity transformation, you'll get the same spectrum. the multipliers I are invariant. And that we'll use, the reason why I emphasize it now is because once we get to periodic orbit theory, one of the beautiful things about it is that all averages we compute will not be in our coordinate system. They'll actually use these invariant quantities. So it doesn't matter what coordinates you use to compute your data. The final calculation of giving predictions from the data will be coordinate independent.